Good morning, class. Today we are going to discuss about the dot product in Rn. First, we'll give the definition of what it means by the dot product in Rn, and then discuss some of its properties. Then we'll mention about the orthogonal and orthonormal basis. So if you are given two vectors x and y in Rn, then the definition of the dot product of x and y is that you multiply x transpose and y. In the sense of matrix multiplication, it means you multiply the row vector and the column vector y. So this is actually just x written in row, right? That's why we use xt. If we multiply row and column, we are going to get this. The length of a vector x is denoted as x inside the pair of vertical line. And that is the square root of the dot product between x and x itself. So if you apply the definition of the dot product for x and x, so y is going to be x as well, then you are going to multiply the x in row and the x in column. So at that time you will have x1, x1, x2, x2, and xn, xn. That's why you have x1 squared, x2 squared, and xn squared. People often use the double lines for the length or the magnitude instead of writing something that looks like the absolute value. We also have the definition of the distance between two vectors, x and y. The distance between x and y is denoted as x minus y, then the length of x minus y. And you can apply the length definition above, right? You dot product x minus y with x minus y, and you are going to have x minus y squared, x minus y squared, and x minus y squared. The angle between two vectors x and y is defined as theta, and it is the cosine inverse of the ratio between the dot product and the product of the length of two vectors. Example number 1. In R2, given two vectors A, 2, 4, and B, 6, negative 3. Compute the dot product of A and B, the length of A, the length of B, distance between A and B, and the angle between A and B. The dot product of A and B is going to be like the matrix multiplication, in which you multiply a row matrix, so you use AT, and a column matrix B. So A, when you write in row, is going to be 2, 4, and B in column 6, negative 3. And so we multiply the matrix here and the matrix here. 2 times 6, 4 times negative 3. We end up having 12 plus negative 12. And in this case, we have the dot product being 0. Next, we are going to compute the length of A. The length of A is the square root of A dot A. And by the formula we have in the previous slide, then we are going to just square the first entry of A and square the second entry of A, and then we add the squares together and take the square root. So it's going to be square root of 20, and that is going to be 2 root 5. Similarly, the length of B is going to be 3 root 5. Next, we are going to compute the distance between two vectors A and B. By the definition, distance between A and B is going to be the length of the difference between A and B. A minus B is 2, 4 minus 6, negative 3. And so that is going to give you negative 4 and 7. Then you can compute length of A minus B. So that is going to be, you square the first entry and add with the square of the second entry. And so in this case, it's going to give you root of 65. Next, we are going to compute the angle between A and B. So the angle between A and B is theta, and that is cosine inverse of the ratio between the dot product and the product of the length of A and of B. So you get to compute cosine inverse of A dot B. 0. So you fill in 0 here. Length of A is 2 root 5 and length of B 3 root 5. In this case, because the dot product is 0, so you don't need to care much about the bottom, but in general, these are going to contribute something to the angle. And so this is going to give you cosine inverse of 0. This is pi over 2 radian or 90 degrees. If you plot the vector A, 2 and 4, this is okay to think of the point A just as the vector OA. And similarly, you can plot the point B and think of it just like the vector OB. What is the length of A? The length of A is in fact the length of the vector that connects the point A and the origin. Similarly, this is the length of B. The distance between two vectors A and B is going to be the distance between the point A and the point B. The angle between A and B is this guy. And in this case, we see and we know that the angle is 90 degrees. Right. Definition 6.3. Two vectors x and y are orthogonal when your dot products of x and y is 0. Orthogonal just means perpendicular in geometry. That means that the angle between the two vectors is going to be 90 degrees. We have 5 properties. The first 3 are very easy to prove. The later 2 properties are very important. If you take advanced math courses, you will use them a lot. The Cauchy-Schwarz inequality, the triangle inequality. The proof of D and E are simple, so I'm going to go over the proof quickly. We are going to utilize the definition of the angle between the two vectors. But this is the same as cosine of theta equal to the dot product divided by the product of the length. This is going to be giving you x dot y equals cosine of theta times the length of x times the length of y. Next, you are going to take the absolute value of both sides. Now, what is the difference between this guy, and the two things inside? Now, you look at this. When you dot product x and y, what you're going to get is a real number, right? You dot product, you get a real number. That is because you just multiply the entries and add the result. So at the end, whatever, it's going to give you a real number. Whenever the inside part is a real number, this notation means the absolute value. Of course, cosine of an angle is going to give you a number. The length of x and the length of y, they are numbers. This means the absolute value. However, when you look at this notation, it means the length or the magnitude of the vector x. And because inside is a vector, you understand that this means the length or the magnitude of the vector inside. If you take the absolute value of the product of 3 numbers here, then this number is positive. It's just the length. This number is also positive, so you can pull it out of the absolute value. However, cosine of an angle can be positive, can be negative. Cosine will be positive if the angle is an acute angle, less than 90 degrees. Cosine is going to be negative if the angle is greater than 90 degrees. So you don't know whether you're going to get positive or negative value here. So you have to keep the absolute value with the cosine. However, you know that cosine of an angle is going to be in between -1 and 1. And so when you take the absolute value, the result is going to be positive, but still less than 1, right? So this guy is going to be less than or equals to 1, which implies that the above expression is going to be less than or equal to x times y times 1, which is the length of x times the length of y. And we have finished proving the Cauchy-Schwarz theorem. The triangle inequality says that the length of x plus y is less than the length of x plus the length of y. We start with the definition of the length. The length of a vector is defined to be the square root of the dot product of the vector with itself. And the vector here is x plus y. You can distribute x into the sum and distribute y into the sum because of the distributive property. Property B, we have x dot x, x dot y, y dot x, y dot y. By the commutative property, which is A, we know that this is going to be equal to x dot x plus 2 times x dot y. And the dot here means the multiplication between the real number 2 and the real number that is the result of computing the dot product of x and y. So in order to avoid confusion, I'm going to erase the dot here, right? And then y dot y. So next, I'm going to use the definition of the length. So we have seen that we define the length of x to be the dot product of x and itself, then taken the square root. Right. So this implies that if you square the length, then you are going to get x dot x. Surprisingly, when you dot x with itself, it's the same as you multiply the length with itself. And so this means that you can go ahead and replace this by the length of the vector x being squared, the length of the vector y being squared. Next, I'm going to apply what we have seen above. Look at this. In the proof of D, we have already deduced that x dot y is equals to the length of x times the length of y and multiply with cosine of the angle between the two. So I'm going to use that here. Right? So from the proof of D, I know that I can go ahead and replace the whole thing here 2 times x length of y and cosine of the angle between them. But then again, we know that cosine of theta is less than or equals to 1. So that makes the whole expression above less than or equals to square root of length of x squared plus 2 times length of x times length of y times 1, which we don't need to write, right? And then plus length of y squared. And so the whole thing here would be the same as length of x plus length of y all squared. This is going to be equals to length of x plus length of y because the root is going to kill the square. All right, anyway, we have successfully proven that the length of the sum of two vectors is less than or equals to the sum of the length of each vector. Now, the explanation for why this inequality is called a triangle inequality. Right? For simplicity, I'm going to illustrate this in 2 dimensions. R2. Suppose you have a vector x, the vector y. If you want to compute x plus y, you will have to draw a parallelogram. And then you are going to have a vector that connects the origin and the other point on the parallelogram. So this is going to give you the vector x plus y. This side has the length of y. This side has the length equals to the length of the opposite side of the parallelogram. And the length of this is x, the length of vector x. So this side has the length of vector x. Obviously, this side, the diagonal, has the length of the vector x plus 1. And in geometry, we have the theorem, very famous, right? In any triangle, if you sum up the length of two sides, it's always greater than the length of the other side. In this case, the sum of two sides are x and y is greater than the other side, which is the length of x plus y. Now, this theorem in geometry gives us the greater than, but we still can get equal. When do we have equality? The equality happens when the triangle turns out to be a flat one. That means vector x and vector y are pointing to the same direction, right? And they are on the same line. Orthogonal basis and orthonormal basis, right? Now, first, let's start with a basis in a k-dimensional vector space. And for the context of this textbook, usually the k-dimensional vector space is going to be a subspace of some other higher dimension Rn, right? Where n is greater than k. K can be equals to n, which is just the special case. An orthogonal basis is actually just first a basis spanning an independent, plus the vectors are all pairwise perpendicular or pairwise orthogonal. Now, the orthonormal basis is a little bit more than orthogonal, right? So it has to be a basis, which means it has spanning property and it has independence property. It is orthonormal, so it is got to be first orthogonal, which means all vectors are perpendicular to each other. And the length of each vector will have to be 1. If the length is not 1, then it's just orthogonal, right? If besides the perpendicularity, you have the length being 1, that's orthonormal. Orthogonal is better than a regular basis, and orthonormal is going to be better than orthogonal. Remember, way back before, if you want to compute the coordinate of a vector with respect to a basis in a vector space, then you will have to express the vector as the linear combinations of the vectors in the basis of W, right? Then this means that you will have to solve a system of linear equations. And from there, you'll be able to get the scalars. That is the solution of the system of linear equations. These scalars are going to form a coordinate vector for the vector x with respect to the basis in W. Now, that is the standard process for a regular basis. If you have an orthogonal basis, you don't have to do that because solving system of linear equation is time consuming. You know that, although we have a very powerful tool, the Gaussian elimination method, to do so, but it's still time consuming. If the basis is an orthogonal basis, then you can compute the coordinates here very quickly by using this formula in theorem 6.4. If you want to compute the ith coordinate, just dot product the vector x and the ith vector in the basis, then divided by the dot product of the ith vector with itself. And that's what the theorem says. So for example, if you want to compute x1 prime, you are going to compute x dot x1, then divided by x1 dot x1. You are going to get x1 prime, the first coordinate of x with respect to the basis of W. Then you kind of upgrade the orthogonal basis to an orthonormal basis. For example, if you compute this, the coordinate, now you know that the length of xi are on 1 because orthonormal, right? Then what it would become is that x dot xi divided by 1, because the length of a vector by definition is the square root of the dot product of that vector with itself. And so if the square root is 1, then xi dot xi without square root is going to be 1 square, which is also 1. And that means that in computing the coordinate for a vector with respect to an orthonormal basis, you only need to dot the vector with the corresponding vector in the basis. And you don't have to worry about division anymore because that's just division by 1. This is a more convenient computation if you have an orthonormal basis, right? Further than that, an orthonormal basis acts just like a standard basis in Rn. I should say that it acts just like a standard basis in W, to be more precise. The reason I say so is that if you have B, an orthonormal basis of a k-dimensional vector space W, right? Then the dot product of two vectors x and y in W turns out to be just the dot product of the coordinate of x and the coordinate of y with respect to the basis B in W. All right, so let's consider an example. Example number 2. Let W being the span of the three vectors in R4. All right, so this is a subspace in R4. Prove that the spanning set is an orthogonal basis for W. So first we need to name the first vector capital X1, the second one capital X2, and the last one capital X3. The spanning set here is, of course, B equals X1, X2, X3. Well, I'm not going to use B at this step because we are not sure if it is going to be the basis or not, right? We need to show that this is going to be an orthogonal basis. In order to prove that the three vectors here forms an orthogonal basis, we need to first show that it is a basis. And it is orthogonal, which means that every vector is perpendicular to the other vectors. You have to first prove spanning, but that is granted, right? So you have spanning for granted because of the way you form W. Now you have to check for independence and then check for orthogonality. In this class, we are going to check for orthogonality. We are not going to check for independence because the fact is that once you have orthogonality, you automatically have independence. And that's what you are going to prove in exercise 6.18. All right. Orthogonal immediately implies independence for you, and that is why orthogonal is so nice to use. Right? For now, I'm going to check for orthogonality. You have to first check if x1 is perpendicular to x2. You need to check if x1 is perpendicular to x3. And then you need to check x2 perpendicular to x3 or not. Now, if you have a set of 4 or more vectors, for example, you have y1, y2, y3, and y4. Then you are going to first check if y1 is perpendicular to y2, if it is perpendicular to y3, and then y4. Then you are going to check if y2 is perpendicular to y3, to y4, and then you will need to double check if y3 is perpendicular to y4. All right, so first, if you want to check if x1 and x2 are perpendicular, then you have to check the dot product between the two vectors. If the dot product is 0, then you have orthogonality between x1 and x2. So x1 dot with x2. Now, as we learned in the definition, the dot product between two column vectors is the same as matrix multiplication, the first vector being transposed and then matrix multiply with the second vector. Then, because we know that x1 is the column vector here, so if you transpose it, you are going to get all these entries written in rows. So you're going to get 1, 1, 1, and 1. Then you multiply with x2 written in column. That is 1, 2, 3, and -6. So now it's just matrix multiplication. You have one row and one column. You multiply the row and the column. And so that is going to be giving you 0. And the dot product being 0 implies that the two vectors are perpendicular. And so we check the first one. Similarly, all right. So this implies that the set here is orthogonal. By exercise 6.18, we have being orthogonal implies that the set is going to be independent. Furthermore, we have the set of x1, x2, and x3 is the spanning set because W was given to be the span of the three, so they are actually spanning W. We don't have to prove anything. So now you have spanning, independent, and orthogonal. So that implies that x1, x2, x3 is an orthogonal basis. And then you can give a name for the basis here. Say it is B. Part B is the vector x here belonging to W, right? You need to check if x is in W. If x is in W, find the coordinate vector for x with respect to the above orthogonal basis, which means that the basis formed by x1, x2, and x3. In order to do this, we are going to utilize theorem 6.4. All right. If x is in W, then x is going to be equals to some a times x1 plus b times x2 plus c times x3. By theorem 6.4, the a is going to be x1 prime, the first coordinate with respect to the basis in W. If you want to find the first coordinate of the vector x, you will need to dot product x and x1, and then divide it by the dot product of x1 and x1. So we have already known x, and we have already known the vector x1. So you're gonna get 8 on the top. Now you have to divide the dot product of x1 and x1 itself. So you're gonna get 4. And so the first scalar, if any, has to be 2. The second scalar b is like x2 prime in theorem 6.4. So you dot x with x2 and divide it by x2 dot x2. Now, if you do all the computation correctly, then x dot x2 is going to give you -50, while x2 dot x2 is going to give you 50. And so that's going to give you -1 as the value for b, if b exists. And then c is x3 prime in theorem 6.4, that is x dot x3. And then x3 dot x3 itself. The computation is going to be 6/6 and then equals 1. All this implies the fact that the coordinate of the vector x with respect to b is going to be 2, -1, and 1. And so you have seen that the computation is way less than solving a system of linear equation to solve for a, b, and c, right? In the previous chapters, we always have to solve the system here to get a, b, and c, and to get the coordinate here. Now the coordinate can be computed very easily if the basis is orthogonal. However, if you stop here and accept that this is the coordinate of x here, then you take the risk of making a mistake. We have to double check if these values, when you combine and compose with x1, x2, and x3, is going to give you x when you sum them up. Sometimes you can compute a, b, and c very easily, but when you double check by compiling a, b, c with x1, x2, and x3 and sum up, you are going to get something other than the vector x. And there is a reason behind that. Before I conclude that this is the coordinate for the vector x, I'm going to go over the process of checking here. If we compute a x1, b x2, and c x3, so this is really giving you the vector x. So this confirms that x is really in W, and hence its coordinate vector is. Now, why do we have to double check? The key is right here. X got to be in W, so that on computation is going to give you the exact X, and these scalars are giving you the coordinate of X. If X is not in W, the computations that you made is not going to give you X. It's gonna give you something other than X. What is that something when X is not in W? Have you wondered yourself? That is the projection image of X onto W. So let's get a picture here. Now let's just say for simplicity, the space W is a plane, right? And in the plane here, you have the basis of two vectors being perpendicular. Now you have a vector x. Then you project it down. By projection, I mean you project perpendicularly. By theorem 6.4, it's actually the x dot x1 over x1 dot x1 multiplied with x1, x dot x2 over x2 dot x2. That's going to give you the second scalar, and then you multiply with x2 scalarly. This is the projection, right? You can imagine when x is on W, if x is in W, then the projection of x is going to be the vector itself. That is why when x is in W, these are going to be the coordinate of x with respect to the basis x1 and x2. However, if x is outside of W like this, then the projection, which is this one, is going to be other than x, right? We check and we see that we have the equality here. This means that x is in W, and that's why we'll have to double check. The double checking part helps us confirm whether the vector is in the space or not in the space. Now, next we are going to discuss part C, find an orthonormal basis for W. We are going to utilize the orthogonal basis. The idea is in the following picture. To find the orthonormal basis, we are going to find the unit vectors, the vector whose length is 1 unit, right? To make sure that we are going to have the three vectors y1, y2, y3 being perpendicular to each other, we are going to utilize what we already had here. We will choose y1 in the same direction as x1, y2 in the same direction as x2, and y3 in the same direction as x3. And we only need to make sure that their length is of length 1. If you want to get the unit vector here, you only need to scale vector x1 back to the vector of length 1. In other words, you only need to divide the vector x1 by its length. Remember, the length of x1 is just 1 over square root of x1 dot x1, and then scalar multiplied with vector x1. Now, if you look at the computations that we had, we know that x1 dot x1 is going to give us 4. So this is going to give you 1/2 times the vector. And so y1 turns out to be the vector 1/2, 1/2, 1/2, and 1/2. Similarly, all right, then we have b prime of the three vectors y1, y2, y3 forms an orthonormal basis for the vector space W. Right? Orthogonality is ensured because y1, y2, y3 are just a scalar of x1, x2, and x3. So the orthogonality will be kept between them. The unit vectors are ensured because we divide every of these vectors by their length. So it's like we scale them back to the unit vectors here. And that's the geometric idea of what is going on behind our computation. Now in part D, we are going to find the coordinate vectors for x and for y with respect to the new orthonormal basis. And then we use these coordinate vectors to double check and see that the formulas in theorem 6.6 are valid. We are going to apply theorem 6.4 for the basis B prime. Remember, B prime is orthonormal, but orthonormal is actually just a special case of orthogonal. So theorem 6.4 is still valid for orthonormal bases. If x is in W, which we have checked, right? And B prime is the basis of W, then x is going to be expressed as x1 prime, y1, x2 prime, y2, x3 prime, y3 according to theorem 6.4. And we also know how to compute this as well. X1 prime is going to be the dot product between x and the first vector in the basis divided by the first vector in the basis, dot itself. Now the nice thing about the orthonormal basis is that when you dot a vector in the basis with itself, you are going to get 1 because this is the length of y1 squared. But the length is 1, so you end up dividing by 1. And so what you actually have is just the dot product between the vector you want to find the coordinate with the first vector in the basis. You're going to get 4. Similarly, all right. And so this means that the coordinate of x with respect to the new basis is x1 prime, x2 prime, x3 prime, and that is the column vector of 3 entries, 4, -5 root 2, and square root of 6. Then we repeat this process for y. We compute the y1 prime. We know that that's going to be, by theorem 6.4, the vector we want to compute the coordinate dot with the first vector in the basis divided by the first vector in the basis dot itself. But again, as I said, this is going to be y dot y1 over 1 squared, right? So this is going to be just this. And then what is the vector y? So the first vector in the dot product, you have to write it as the row vector or the row matrix, right? And then the first vector y1, right? The computation is going to give you 2. Similarly, you are going to get y2 prime is the vector y dot with the second vector in the basis. Straightforward computations is going to give you the value being 0, y3 prime, y dot y3. Right. If you do things correctly, you should be able to get square root of 6. And so this implies that the coordinate of y with respect to the orthonormal basis B prime is a triple 2, 0, square root of 6. Right? Remember, vector y is a vector of 4 entries, of 4 tuples. But its coordinate is just a triple. Right? So the vector and its coordinate with respect to a basis is different. Now double check if theorem 6.6 is valid. Theorem 6.6 says that if you consider the dot product of two vectors in a vector space, right, which is a subspace of Rn, in this case, that is R4, the regular dot product turns out to be the product of the coordinates and then sum up. All right, so that means we have to check x dot y. So x is the vector of 4 entries, 2, -2, 0, and 8. Y is the vector of 4 entries, 2, -1, 2, and 1. So when you dot the 2 here, you're gonna get 2 times 2, which is 4, then -2 times -1, which is 2, and then 2 and 0, that is 0, and then 8 and 1, which is 8. You sum them up, you get 14. Now, if you check x1 prime, y1 prime, x2 prime, y2 prime, x3 prime, y3 prime, in other words, it's just this. The coordinate of x with respect to b prime dot with the coordinate of y with respect to b prime. Because you are going to multiply first entry with first entry, second with second, last with last, and then add them together. So this is going to be, right, so back here, 4, -5 root 2 and square root of 6. And then you multiply with coordinate of y, 2, 0, root 6. 4 and 2, that is 8. -5 root 2 and 0, how easy, right? Root 6 and root 6, so that's going to give you 6. And you sum up and you get 14. They are really equal. So now let's go back and give the proof of 6.4. It says that if we have the vector x being in a space that has an orthogonal basis, then the coordinate of x with respect to the basis of the space is going to be computed by the formula here. First, because x is in W and W has a basis B of k vectors. Then, being a basis means being spanning for W, so any x can be expressed as a linear combination. I dot the vector x with the vector x1, the first vector in the basis. Now I'm going to utilize the distributive property of the dot product, which is property B. We can distribute the dot product into a sum. But then you will wonder, this dot product is distributed from the left of the sum. What I have here is the dot product from the right of the sum. Can I still distribute it? The answer is yes, because we have the first property, property A, the dot product is commutative, which means you may switch the x here from in front to behind the sum. And so that is going to give you the same thing, right? So by property A, the distributive property can be applied from the left and can also be applied from the right. By property A and B, you have this being distributed to x1, this being distributed to x1, and you have this. Now you use the scalar property, which is property C, right? You can pull the scalar, this is just the scalar, you can pull the scalar out, and that leaves the x1 dot x1 inside. And so you pull the scalar out and you have x2 dot x1. And then you pull the scalar out, you have xk dot x1. Now it's time to use the orthogonality. The orthogonality says that if you dot any pair of different vectors, you're gonna get 0 because they are pairwise perpendicular. So you're gonna get 0 here, 0 here. The only thing that is left is this guy, right? And so this implies that x dot x1 is equals to the first coordinate multiplied with x1 dot x1. And so by dividing, you have proven that the first coordinate is going to be x dot x1 divided by x1 dot x1. Similarly, we are going to have the same thing for x2. After k steps, right, we are going to get x dot xk over xk dot xk. 6.6 is a little bit more complicated, but it's actually just the same idea here. And I'm going to just prove the first part. The second part is straightforward. So first of all, we have x being in W, and W has a basis, right? So that means you can write x as the combination of the vectors in the basis. Similarly, you are going to have y being written as the combination of the vectors in the basis. So the dot of x and y is going to be just the dot between the combination for x and the combination for y. Now we are going to use the distributive property, property B. We are going to distribute each term here in the first sum to the second sum. So we are going to get x1 prime capital X1 dot with y1 prime capital X1. This and this. Then we have x1 prime x1 dot with y2 prime x2. And then dot dot dot. And then this one with the last one. And then you repeat for the second term here. This with this. And then this and this. Dot dot dot. And then this and the last one. And then dot dot dot. And then the last one being distributed. Now, everything seems scary, but if you observe, then this term is going to be 0. Why? Because you know x1 and x2 being perpendicular. So even if you give this vector a scale and this vector a scale, their scales are also perpendicular, and so the dot product is going to be 0. So this is going to be 0. All of these are going to be 0 except the diagonal, because on the diagonal it is where you have the vector dot with itself, x1 with x1, x2 with x2, xk with xk. Oh, by the way, this is xk. Sorry about the confusion here. This is xk. All right, this implies that x dot y is equals to x1 prime capital X1, y1 prime capital X1 plus x2 prime capital X2, y2 dot y2 prime capital X2 dot xk prime capital Xk dot yk prime capital Xk. Then we can utilize the scalar property of the dot product to pull out the scalars here and here. You are going to get 1 because you know that these are going to be the length of the vector being squared, right? The length of the vector is the square root of the dot product. So the dot product is the square of the length, but length is 1. So all of them are going to give you 1. And so this implies that x dot y is x1 prime, the coordinate of x dot with the coordinate of y. And we are done. Once we are done with the dot product, the length formula is going to be just a direct application of the dot product.